Welcome to this explainer. You know, when most people look at a modern drone, they see a chaotic cluster of confusing circuit boards, spinning plastic, and a tangle of wires. It kind of looks like magic, right? But today we're going to completely reframe that perspective. I want you to look at a drone not just as a simple machine, but as a complex, highly evolved electronic organism.
Okay, let's dive into this. How exactly does a lifeless piece of carbon fiber perfectly defy gravity? How does it fight off turbulent crosswinds and somehow maintain a high-definition video link from miles away? Well, the answer is a beautiful problem-solution arc where multidisciplinary engineering and pure math step in to defeat gravity, wind, and signal loss.
To make sense of it all without getting bogged down in the textbook definitions, we're going to follow a biological roadmap. We'll look at airframes and aerodynamics as the skeleton, brushless motors as the muscles, electronic speed controllers as the nervous system, the flight controller as the brain, and wireless and positioning as the senses.
All right, part 1. Airframes and aerodynamics. The skeleton.
A drone's fundamental geometric layout completely dictates its physical capabilities. It's the foundation of everything, and there are massive aerodynamic trade-offs depending on the skeleton you choose. Take multirotors, for example, like your standard quadcopter. They offer incredible hovering versatility, but because they have to actively force air down just to stay aloft, their cruise efficiency is basically zero. Fixed-wing setups, like traditional airplanes, are the exact opposite. They use passive airfoil lift for amazing cruise efficiency, but they literally can't hover at all. And then we have hybrid VTOL platforms, which try to blend both, using symmetric airfoils to manage the incredibly complex transition from hovering to forward flight. To support all these intense aerodynamic forces, the physical construction has to be absolutely perfect. Modern professional drones aren't just using standard plastic. They use CNC precision-cut 3K twill-weave carbon fiber. We choose this specific material because it yields a massive 30% weight reduction compared to aluminum, while offering extreme high-G impact resistance. But there's a problem. Carbon fiber is super stiff, meaning it transmits vibration like crazy. That's why we integrate TPU inserts. Think of them as shock-absorbing sneaker soles for your drone. These viscoelastic dampeners absorb acoustic vibrations before they can rattle the drone's ultra-sensitive internal sensors.
Moving on to part 2, brushless motors, creating magnetic magic, the muscles.
Get this. 30,000. That is the upper lifespan in hours of a modern brushless DC motor. This is our propulsion system, the mechanical muscle converting stored chemical energy right into physical thrust. Older brushed motors would literally destroy themselves through physical friction and carbon arcing, usually tapping out around 5,000 hours. By electronically commutating the motor and totally eliminating those physical brushes, we don't just eliminate friction, we also get rid of electromagnetic interference and hit electrical to mechanical conversion efficiencies up to 90%.
Now, what's really interesting about this slide is how motor topography comes down to dynamic scaling laws. If you want high torque at low speeds to spin a big propeller directly, you use an outrunner. The rotor spins on the outside, which maximizes the air gap radius and gives you a massive torque arm. But if you're after blistering acceleration, you go with an Inrunner. Because the mass is concentrated near the center, it has minimal rotational inertia and can spin up to 50,000 RPM. Though you'll usually need a mechanical gearbox to actually make that speed useful.
You'll often hear engineers throw around the term kV. Simply put, this is the motor's velocity constant. It's the RPM the motor will spin for every 1 volt of electricity you feed into it. There's a strict engineering trade-off here, kind of like the gearing in a car. Tiny, low-voltage microdrones use a very high kV to get the insane speed required for small props. Conversely, heavy-lift industrial drones use high-voltage batteries paired with a low kV motor. This generates the massive torque needed to efficiently swing a very large propeller.
To actually make these muscles contract, we rely on some pretty deep math. The stator inside the motor generates a mathematically perfect rotating magnetic field using 3-phase alternating currents. The resultant magnetic flux maintains a constant magnitude of exactly 1.5 times the peak flux of a single phase. The permanent magnets on the rotor are continuously chasing this rotating field. It's honestly exactly like a greyhound chasing a mechanical rabbit around a track, and that endless chase produces perfectly smooth, continuous torque.
Okay, let's look at part 3. Electronic speed controllers, the drone nervous system.
If the motors are the muscles, the ESC is for sure the nervous system. It acts as the high-power actuator, translating low-voltage commands into precise alternating currents. Now, most drone motors don't actually have physical position sensors inside them. Sensors add weight and they break easily. Instead, the ESC cleverly uses a principle called back electromotive force.
As the motor spins, it acts like a little generator, pushing a tiny amount of voltage back to the ESC. When you first start the motor, the ESC does this open-loop blind stepping just to get things spinning. But once the rotor accelerates, the ESC listens for the zero crossing point of that back EMF on the inactive wire. The second it detects that, it snaps in the closed-loop sensorless tracking, timing the magnetic pulses with absolute perfection.
Let's move to part 4 and see how this all builds together: the flight controller, the brain, and PID loops.
This is the brain, the central processing unit running the high-level math that actually keeps the aircraft stabilized in the sky. 8,000 high-end flight controllers are running their closed-loop stabilization math up to 8,000 times every single second. That's 8 kilohertz. They do this by rapidly reading spatial data from microscopic MEMS gyroscopes right on the board, detecting even the tiniest gust of wind way before the human eye could ever perceive it. It's literally reacting faster than a human reflex. To process all this data, the brain uses an advanced control theory concept called a PID loop, but we can easily translate this into a biological concept. Proportional is how the drone reacts to a present error, like a sudden tilt. Integral is how it remembers past error, say compensating for a constant steady push from a crosswind over time. And derivative is how it predicts future error, acting as a dampener so the drone doesn't violently overcorrect and just shake itself apart. So it reacts, remembers, and predicts. But wait, there is a catch here. Sampling your sensors at 8,000 times a second is completely useless if your nervous system has a communication bottleneck. This is exactly why modern drones mandate 32-bit ARM Cortex processors and digital protocols like DShot 600. DShot 600 fires off data packets to the ESC within a tiny 26.7 microsecond window. This guarantees there is virtually zero latency between the brain recognizing a problem and the muscles reacting to fix it.
Of course, different brains have different personalities, defined by their software architecture. Betaflight is all about raw speed. It runs bare metal code for incredibly low latency, which is absolutely perfect for drone racing. Autopilot, on the other hand, is the heavy thinker. It runs a real-time operating system to handle massive computational payloads for fully autonomous surveying and complex waypoint navigation. And then you have iNav, which sits right in the middle, offering great manual control, but cleverly stepping in with GPS rescue if you happen to lose your bearings.
Finally, Part 5, Wireless and Positioning, the senses. This final system layer is what gives the drone its eyes and ears, providing telemetry, spatial positioning, and video transmission. To keep the pilot perfectly connected, drones use advanced RF technology. Take ExpressLRS, for example. It's a wildly popular open-source link that boasts sub-1.5 millisecond latency. It achieves insane range using LoRa chirp spread spectrum modulation. What that means is it can literally decode control signals that are 20 decibels below the thermal noise floor, which is the equivalent of hearing a whisper in the middle of a heavy metal concert. Alternatively, a system like TBS Crossfire is proprietary and trades that bleeding-edge latency for highly robust, bidirectional telemetry, sending massive amounts of sensor data back to the pilot. So, the crucial point is that choosing how your drone sees the world involves massive engineering trade-offs. Analog and HD0 provide fixed, constant latency. The image might get staticky, sure, but it never lags, which is absolutely mandatory for high-speed flight. On the flip side, the DJI-04 system uses variable latency with two-way packet confirmation. The latency might jump around slightly, but in exchange, you get breathtaking 1080p high-definition video that can penetrate through solid obstacles up to 26 kilometers away.
But what happens when the drone goes indoors and its senses are totally cut off from GPS satellites? Well, it uses alternative senses. It relies on an optical flow sensor, which functions exactly like the laser mouse on your computer desk, literally watching the pixels of the ground move beneath it to calculate its exact speed. It pairs this with a time-of-flight laser rangefinder, shooting infrared lasers at the floor to measure its altitude down to the millimeter.
Outdoors, however, it's a different story. We use GNSS. Now, standard GPS is great, but it has a margin of error of a few meters. For industrial applications, we step it up to real-time kinematic, or RTK mapping. By using a local ground station to correct for atmospheric delays in the satellite signal, RTK utilizes carrier phase tracking to achieve a massive leap in accuracy, shrinking positioning errors from meters down to a mind-blowing 1 to 2 centimeters.
And all of this brilliantly illustrates our core thesis today. A drone requires profound multidisciplinary integration. You can't just slap parts together and hope for the best. Think about it. If your carbon fiber skeleton is too rigid, it causes structural resonance. That mechanical noise travels to the gyroscope, causing sensor aliasing. The flight controller then sends panic signals to the nervous system, the motor muscles vibrate violently, and the entire system just falls out of the sky. The mechanics, the electromagnetics, and the processing power must be perfectly co-engineered in absolute harmony.
We've explored the skeleton, the muscles, the nervous system, the brain, and the senses. So I want to leave you with this final thought. Next time you see a drone hovering perfectly in a turbulent crosswind, seamlessly performing thousands of mathematical calculations every single second just to stay alive, ask yourself, are you looking at a simple machine or a highly evolved electronic organism? Thanks for joining me on this explainer, and keep questioning how the world around you works.